So welcome back. We are kind of behind this time in the schedule, so it took us some time to finish the exercise, but we also started a little bit late. So let's plan in the remaining 30 minutes or so to take one big exercise where we're gonna apply loops, we are gonna apply plotting, all of this inside the function. So that should be a compilation of all what we have learned so far. But before this, and as you know, kind of fun thing, and which I will leave it to you to find out maybe by searching online. So that's the function that we wrote before we actually leave to the break. I will leave it to you as a fun exploration. You need to look it up online. How, as one of the outputs of this function, I can plot the XYZ coordinates, so XYZ, and maybe sketch the point that the user gave to the function in cylindrical, and you change it into Cartesian. And then how do you draw a vector, a position vector, starting from the origin to that point? Although this is a very simple visualization, but it's good to learn on your own. I mean, one skill that's very important is to learn how to search online, the online documentation, the online forums of MATLAB. Please try to do it. If you couldn't, next time we can look it up together and try to do it together. But at least you have to learn this skill. You know, the idea is simple. I have a point. I want to sketch three axes, X, Y, Z, and, you know, to put a position vector in a space that points from the origin to that point. That would be fun exercise to do on top of the function that we created. But now I want, first you guys will work on your own, and then we come back to the main room and exercise this together. There is this, I hope you see my screen now. There is this seemingly long exercise that's called the hyperbolic cosine function. The hyperbolic cosine function, which is basically the cosine function. It's basically be evaluated using an infinite Taylor series in this fashion. So cosine x equals 1 plus x squared over factorial 2, x4 factorial 4. And we are asking you to write a function that needs as an input from the user the value of x, right? And the acceptable true percent error from the user, and then it calculates cosine x, right? Using the above series until the acceptable error is satisfied. Let me explain this point. Maybe that's the only vague point that we can illustrate. So the acceptable true percent error. What is the true percent error first? What is, let me give it this notation, epsilon true. It is your approximate value, your approximation, okay, minus your true value, which you might wonder, where are we gonna get the true value of the cosine? Just use the built-in function of cosine in MATLAB. That's gonna be your true value. Divided by the true one more time, and then you multiply by 100 just to make it a percentage, right? So if you imagine calculating this error after you take one term of the series, just one term, and suppose that x equal, you know, x equals 7, for example. So suppose x equals 7, and I'm gonna take one term of the series. In fact, let me do this in MATLAB itself. I wanna calculate the true error in this case. If I take, let me go up even like this. Clear all TLP, just as a test for the error. If I want the approximate value is 1 minus the true value. We said let's make x equal 7, so it's gonna be cosine 7 divided by the true value is cosine 7, and then multiply this by 100. Take the absolute value first, and then multiply by 100. So if we do this, the error is gonna be 99%. Let's go back to the series, if you take one term alone and you try to calculate cosine 7, then the error is going to be 99%. Let's say we take two terms. What do we mean by taking two terms? Well, it's going to mean that I'm going to approximate cosine x approximately equals 1 plus x squared over factorial 2. Factorial 2 is 2. So let's test this. Let's actually test how much error is going to come if we take two terms. I'm going to go back to my MATLAB. So instead of 1, my approximation is going to be 1 plus 7 squared divided by 2, right, which is factorial 2. Let me make sure I'm doing the brackets correct. Let's try to calculate the absolute value here. The error is going to be 95%. So it improved. You can keep going. You can keep adding more terms. So the next term is 7 power 4 over factorial 4. In fact, x could be any number. X could be 10, 20, 21, 22, 23, anything, right? The goal is that you want to compare how many terms of the series are needed to achieve certain error. For example, if I tell you, keep calculating cosine x until the true error is less than 1%. So you need to create some sort of looping that tries one term and calculate the error. If it is less than 1%, then we are good. Maybe we are not, because we tested and it was like 99%. So you take two terms, right, and calculate cosine 7 again. Calculate the error again. If it is less than 1%, it's going to stop. If not, it's going to take another term, and so on and so forth, until the error becomes less than 1%. Then it's going to stop. If you connect this to what we have learned in the previous sessions, there is some sort of looping here. I need to loop to take more terms until I meet certain criteria. That's the flavor of a while loop. Okay, so we are going to calculate cosine x basically using the above series until the acceptable error is satisfied. The user is going to give you the acceptable error. Okay, make sure that the function does the following. First of all, it has to store I don't know what's this. It has to store that error in an array for each number of terms. Like, for example, if we go back to MATLAB, for one term, it should store in the memory in an array that's called error, for example, or error t, which is the true error, 99%. The second element of the array is going to be 95. The third element of the array will be the third error when you take three terms, and so on and so forth. So you need to store these errors in an array. The other thing, you need to plot that error as a function of the number of terms. Like, for example, so far, for the case of x equals 7, I could put two axes. Here is the number of terms, and here is the error. When I had one term, if you remember what was the error, it was like 99%. So I can put a point here right at 99. When there was two terms, the error was 95. Possibly if there are three terms, the error is going to decrease. So it's going to be a decreasing curve. We want you to plot the error as a function of the number of terms, and make sure to label the x-axis, the y-axis, add a legend, and use a logarithmic plot. So on both x and y axis, we have had a chance to look at these in a previous session. So you need the log function, to make it logarithmic on x and logarithmic on y. And then there is this is nice thing which is called tick-tock. Tick-tock allows you to time your code. Timed your code means know how many how much time does it take on your computer. And I will actually show you this in a second now, before we go into breakout rooms and try on our own. And then we need to run the function for the case x equals 1. In fact, let's actually do something different, since the one that we worked in the exercise, let's try the case x equals 7, the one that we worked together here. and with an acceptable error of 10 to the power minus 13%. That's a very, 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 very tiny error. Okay, 10 to the power minus 13%, very small error. Okay, and then report the final plot and the time of the calculation using TikTok. Okay, and then from the log, okay, let's actually do this. If we finish part B, C, A and B, C is easy, and we can do it together actually here in the main room. But just to give you some orientation about the structure of the function, it's a MATLAB function. So let me go back to MATLAB and remove all these annotations. Guys, this is a non-trivial exercise. It's a dense, but it combines everything we have learned so far. It's gonna contain loops, it's gonna contain plotting, and everything is inside a function. Okay, so it's quite instructive example. So I'm gonna open here a new file. There will be a function here. Let's, for example, call it my cosh function, and it needs as an input from the user. It's gonna need the value of x that's trying to calculate its cosine. It's gonna need also the acceptable error in percent. Okay, I don't think it needs anything else. What it's gonna output, well, it's gonna output the value, our estimate, let's call it this way, or it's gonna actually output the what it should output. So we agreed it's gonna store the error, it's gonna do plotting. Do we need to okay, let's make it to calculate the true error for us as an output. And it's gonna make a graph, right? So the graph, you don't put it here in between brackets. You are gonna put it as a plotting inside the function itself. So it's gonna output the true error, and that's it. I don't think it you want anything else from it. What's the value of the true error that you achieved? Do we need something? No, that's good enough. Then maybe you need a tech here and a talk here, because between tech and talk, and that's how you use tech talk function. Between tech and talk, the MATLAB is gonna count how much time it needs on the computer, and it's gonna report it on the command window. So guys, your code has to go between tech and talk. So this is to find out how many seconds. It's gonna run in seconds. How many seconds your code is going to use or needs to run. Okay. All right. So I will leave you. I'm gonna save this here. I will leave you in breakout rooms. Guys, the exercise is a little bit dense, but please try it as much as you can. And when we get back here to the room, we will try, to go over the mistakes or any that you guys went through in the breakout rooms. So let's stop this,